welcome you all. In the last class, we have covered about symmetry in three-dimensional lattice. What we will do is we will have a recap of what has been done, some of the significant points. Then we will go ahead. So what I am planning to do essentially is to consider the point group 4 mm. 4 mm, the way in which it can be represented, or the way in which it is represented in the International Union of Crystallography, is using stereographic projection. In the stereographic projection, essentially what is being done is a circle which is being shown, which is the equatorial plane, onto which the poles are getting projected. If you take any one of these poles, around this axis, if you give around the z axis a fourfold rotation, this will by 90 degree it will come here, another 90 degree rotation it will come here, another 90 degree it will come here. And if you apply a mirror across x or y direction, any one of the direction, let us see along the x direction we place a mirror, then this point gets reflected here, correct? That is, this point gets reflected here. From here this point will get reflected here, this point will get reflected here, then this point will get reflected here. So already we have all the reflections, that is the operation of 4 and a mirror, 8 points have been generated. And if I put a mirror across this also, it is essentially the same thing, this operation is redundant. So all the symmetry elements which we can see it. Whereas this point has been put at a position where there is no symmetry is associated with it. There is another way in which the same stereographic projection can be shown, and which is being shown in international crystallography, is by showing only the symmetry elements which are associated with it. Now if you look at it, there is a fourfold rotation is there. So fourfold rotation is represented with a square which is at the center. The mirror is shown as a thick line. So this line represents mirror along y axis, this represents mirror along x axis. And when this has been done, if we look at in these two directions, in this direction as well as in this direction, another 2 additional mirrors have been created. That is exactly what is being shown. So we can show the same symmetry elements either by showing just the symmetry elements which are there on the stereographic projection, all the symmetry elements, or we can show the position of a general point, because in a general point also all the symmetry elements have to operate upon it to generate the full position of the equivalent position of that point which has been placed at the general position, right. The same thing is being shown here, around a particular point, how it is getting, different positions are getting generated. Now suppose I put this point not on a general point, suppose I put it on one of the symmetry point here, then what happens? Then by mirror across it, it will be reflected here. By a mirror across this, it will be reflected here. These points also has got a fourfold rotation and a mirror is also there. So all the symmetry elements we are in, but the number of points are now 4. The same along 110 plane, when a mirror is being kept, it is being shown. Suppose instead of putting the point on general point or these special points, if I put it at this one which has got the maximum symmetry at the center, then I require only one point, because around that point all the symmetry operations leaves that point invariant. So only one point is good enough to show the full symmetry. So what are the position of these points are the planes normal to it, that is what is shown in this one. So this shows the symmetry at which the point has been placed, that is where only one fold symmetry is there or no symmetry, and then 8 equivalent positions will come. And if you put it on any symmetry element, that symmetry element has got how many? Mirror, because reflects from one to the other. So its symmetry is 2. So 8 by 2, only 4 points are required. So the position of the 4 planes are being shown. In this case also, again only a mirror we put it, so it becomes 4. Here if you look at it, 4 and m is there. So it's 4, so it becomes 8. So you divide it, that's only 1 point is required to represent the full symmetry. So where exactly the point can be placed to generate all the symmetry is given in this table. A similar table will be given in space group diagram as well, like what has been given for point. This is a point group representation 4 mm, because we have only around a point which we have considered. Okay. Now, as I had mentioned earlier, there are 32 point groups are there. Okay. They are distinct point groups. So this way, the way it has I had shown earlier, we can take any general point on a stereogram and generate equivalent points. Okay. If we do that by these symmetry operations, we will be generating points or stereograms which are distinct from one another, only 32 are going to be there. Any other combination of the point groups, what are the point groups which are there in a material, or a point groups which are possible in 3 dimension? Okay. Basically the operations are 1-fold, 2-fold, 3-fold, 4-fold and 6-fold, mirror and roto inversion of that, and their combinations. That is how these 32 point groups have come. These point groups, depending upon the type of symmetry elements which are associated, they are classified into 7 crystal systems. Okay. So if we look at it, the point group which is being shown on the left hand side corresponds to a minimum point group which this system will have. The point group which is shown on the right hand side, that is in the background, which is pink or whatever is the color you call it, that shows the maximum point group symmetry of the crystal. Okay. So lattice always shows the maximum point group symmetry. So the once 1 bar is the maximum point group symmetry for a triclinic. For a monoclinic lattice, if you look at it, the point group which will be 2 by m. Orthorhombic structure, the point group will be mm. Like this we can see it, correct? Another important thing which you have to see it is that the 3-fold rotation comes in trigonal as well as in cubic. Okay. And here we can, that here we have written as 3-2, here we have put it as 2-3. Okay. There is some convention which is being followed. The convention is that if the 3-fold rotation has been put as the first letter in this 3-letter representation which is we are following it for representing point group, then it is a trigonal. If the 3-fold rotation is put at the second position, then it is always a cubic system, right? And similar to that, some of the symmetries which are shown here are not the full symmetry. Like here it is m 3 bar m, for cubic it is given. Actually the full symmetry operation is, it's essentially 4 by m, this m it corresponds to 3 bar and 2 by m. And if where it is being written for tetragonal 4 by m mm, it corresponds to 4 by m, 2 by m and 2 by m. Okay.
Can you explain it for cubic, m3 bar m for a cubic lattice?
Yeah, cubic lattice.
m3 bar
m 3 bar m is a convention which is being used to represent the maximum symmetry element. The details of it, if you look at it, what all symmetry elements are there? 4 by m, -3, 2 by m. Okay. The question which arises is, forget about that structure itself. Why we use only 3 symmetry elements which are being used? That is the first question, right, which comes into the mind. If we look at a crystal which is tetragonal 4-fold rotation, the 4-fold rotation contains 4-fold rotation, 2-fold rotation and 1-fold rotation. These are all the symmetry elements which are present. In this case, when we try to represent it, we represent only with, if it is only rotation which is available, what is the maximum rotation which is there, only that is used to represent. Similarly, if it contains a combination of rotation and a mirror, okay, then we may have like 4 mm if we take it. 4 mm if we try to take it, then 2 mm is going to be there, 4-fold rotation, mirror, 2-fold rotation, 1-fold, all these symmetry elements are going to be there. We can say that this entire thing combination is going to be there as the symmetry element, one way to represent it. Then it becomes very untidy and it is very difficult to understand. Then a convention which is being followed is what all we should represent to tell that these are all the basic symmetry elements which if we operate upon it, upon the system, almost the full symmetry can be generated. That is the way, it is a convention which is being followed. So when it is written as M 3 bar M, essentially this means that actual symmetry is 4 by M. That is why I mentioned that one should, when we put that 4 by M mm for tetragonal, it is actually 4 by M, 2 by M and 2 by M. That is along, and why we use 3? Because in 3 directions are used, because in a space if you have to represent 3 directions have to be used. What are the 3 directions which are being used? There again a convention which is being followed, okay, because I have not talked about it, which direction is being followed now, okay. In this table I give that, that information is given. Triclinic, that is 3 letters are being put, 3 symmetry elements are being written, right. This primary means the first one, secondary is the second one, tertiary is the third. Monoclinic 0 1 0 is chosen as the B axis, that is what is being represented as the first letter. Let us take orthorhombic. Orthorhombic if we take it 2 2 2, okay, mm2, these are all the 3 symmetry elements which are there. So the first letter shows 2-fold symmetry along 1 0 0 axis, then 2-fold symmetry along 0 0 1 axis, 2-fold symmetry along 0 1 0 axis, correct, all the 3 letters. If you take tetragonal, then the first letter represents 4-fold is symmetry along 0 0 1 z direction, then the another one is symmetry along x or y direction, the second letter. The third letter represents symmetry along 1 1 0 direction. This is a convention which is being followed to represent it. Only if we understand this convention, we know what the rule is which is being followed, then only we can do all the symmetry operations, correct. So similarly for cubic, okay, the first letter represents along 1 0 0 or 0 1 0 or 0 0 1, okay, what is the symmetry operation which is present. The next letters represent symmetry operation along the body diagonal. Then the next one represents the symmetry along 1 1 0 direction, right. So now it is clear how you can correlate it and then try to find out the different symmetry elements, right. Okay. Then I mentioned also about space groups. What do we do in what is a space group? Space group is nothing but, okay, a combination of various point group symmetry operations, okay, alone or together, okay. Then if it is acted upon on different lattice points, what is the type of symmetries which are generated? On the basis of the type of symmetry which are being generated, we find that distinctly there are 230 groups are possible. That is, when we generate these space groups, essentially what we are doing it is, this is being done around a lattice. That means that now we are generating crystals. What all different types of space groups which we can have for crystals, or with symmetry, what all the types of symmetry which crystals can have, only 230 types which we can have, okay. Now we will look into some of these symmetry elements. I had explained in the last class about screw axis, okay. Screw axis is like the glide which I had, we had represented it, okay, in the first lecture. Now what we can do it is that from one point to another point, like when we go from here to here, this is a one asymmetric motif and it's starting from here, okay. And along this axis it has a 6-fold rotation is there. If it is just a 6-fold rotation, around this direction itself all the motif would have been there. Then an identical point would have come where all the 6-fold, all the motifs would have been placed there. In many structures, especially in chemistry, organic chemistry, okay, you can see that from this position to this position when it moves, the motif is placed at different positions but it is rotated and there is a translation is also there. So from this motif to an identical position it comes at some particular translation. That translation could be a multiple of the lattice translation vector. It need not be one translation vector, it could be a multiple also. These sort of symmetry elements which are arising in the lattice is called as the screw axis. Okay. This for a twofold rotation if we consider, we can have only one screw axis can be there and it is represented as 2, 1. Okay. The 1 represents that how many times it is repeated. Okay. 3, 1 if we put it, it is essentially 3 times it is repeated but the pitch will be 1/3. From this we can make out of the lattice parameter or the translation in that direction, translation vector in that particular direction. Okay. That is, if we take 4-fold 4, 1 means that if a translation vector in the direction is A, then the pitch which after every rotation it makes will be A/4, correct? And if we mention this as 4-2, this means that the pitch is going to be A/2 but the rotation is 90 degree. By 90 degree you are rotating it but translating it by A/2. Okay, that is what essentially it means. Okay. This way we can have this much number of additional symmetry elements are possible. But this is because here we are combining a translation and a rotation, right? So similarly, this also I had mentioned earlier about the glide. Okay. So if you look at the what are the glide axes which we have, okay, A glide, B glide, C glide, and then along the face diagonal we can have a glide that is called as a represented by a symbol N. Then we can have a glide along the body diagonal, then it is designated as D. Okay. Then what will be the translation vectors, that is also being given. Okay. So now if we look at it, what are symmetry operations which we can have in a 3-dimensional space group, 3-dimensional lattice. One, rotation symmetry we can have. We can have a mirror symmetry, all the rotations. Inversion, we have a roto inversion, okay. Then we have a glide A, B and C and N and D. Then these are all the types of screw axes. Now if we can see a combination of these various symmetry elements, what are the distinct types of distinct groups which will be formed? That number is only 230. Okay. Okay. When we look at International Union of Crystallography table, okay, or any crystal structure in 3 dimension, if we have to represent it, how do we go about and represent? Okay. 3-dimensional structures representing it directly like that and drawing a figure of a cube or a tetragonal structure and then trying to mark the symmetry elements is going to be very difficult to understand it, correct? As far as point group symmetry is concerned, we found a way out by using a stereographic representation. Here the only way it can be done is that, like in what we do in engineering drawing, if any three-dimensional structure has to be represented, we take a plan and an elevation. Like if you take a monoclinic structure or an orthorhombic structure, a plan and an elevation, if we take it and put projections of all the symmetry elements which are present at different positions, it can be represented. Okay. That is what essentially is being shown. Like you take this case of a body-centered tetragonal lattice. In this one, this is at a position which is half, half, half. So I can represent this by a square. Okay, that is what essentially it is being done. I had just marked the axis also. And this 0 means that it is at the 0th layer or 0 position. Then this position at the middle is just put here and put half. What it half means is that with respect to this layer, it is at a half position upwards. Okay. This is the one way in which it is being represented. Especially when we have a glide axis and all the glide or screw axis comes into the picture, we find that atoms are shifted from one plane to another position. Then this sort of representation has to be used to represent them. Okay. And we know that in a crystal, as we have looked at it earlier, okay, the crystal itself can be identifying the pattern which is repeating itself or the motif. We can generate a lattice points, and the smallest, the three lattice translation vectors we can identify. Then we can construct a unit cell. That unit cell itself can be assumed to be repeating itself to generate the three-dimensional lattice. That way also we can look at it. So this three-dimensional unit, okay, and since it is repeating, if we find out what all symmetry elements which are associated with that, then we have got complete information about the symmetry element, how they are distributed within the complete lattice. We have that information, because applying a translational symmetry, we can generate all of them, correct? So that is essentially what is being done. Okay. If you look into International Table of Crystallography, the information which they give is that the first is what is the crystal system. That information will be given at the left hand. I had shown it here for 3 structures. Okay. So each page is an orthorhombic structure, and this shows what is the point group symmetry which is associated with that lattice. Okay. And this is the space group symbol. Okay. When we put the space group symbol, what we have to do it is that whether it is primitive or it is body centered or tetragonal, this symbol will change. P, if it is body centered, it will be I222. If it is face centered, it will be F222. Like that it will come, correct? And then here a detailed of the various symmetry elements are being given for the orthorhombic structure, and then this number 16 is given. Number 16 means that some few pages it is being represented in sequence 1 to 230 it is being represented. So this is given as the 16th figure representation. Okay. Like here, if you look at this particular structure, orthorhombic structure, the point group symmetry MMM, okay, space group symmetry PMM, the number is 47, and this is the details of the space group symmetry P. This M means the 2 by M, 2 by M, 2 by M. Okay. This is all acting along each one of the A, B and C axis, correct, for orthorhombic structure. So essentially this gives complete information about the crystals, whatever is required, what is the type of system, all this information is given. Similarly, this is for a monoclinic I have taken, where it is point group symmetry is 2 by M. Because you know that this glide and screw, okay, they are associated with translation, okay, they are not called as point group symmetries. After giving all these details, like what is being given for a, I have taken the monoclinic structure P2, okay, because triclinic does not have any symmetry, so I thought that I will just take a monoclinic structure. That means the twofold rotation is going to be there, correct? this is the A axis, this is the C axis, this is the B axis, and along the B axis only the twofold rotation is. B axis is perpendicular to a figure. That is, twofold rotation means that it can be represented by a symbol with the ellipse. Then around this lattice point also we should have identical. Around this point and this point it should be there. That is, if I put a motif, this is what we have shown, the projection of the lattice, okay, along 0, 1, 0 plane. So on this plane, now if we see it, this is where at a general position a motif is being shown. In the International Union Table of Crystallography, the motif is being shown as a open circle, asymmetric motif. And the plus means that since this has got only one symmetry axis, the coordinate is not fixed, where to take the origin. Origin can be taken arbitrarily. From that point, there is a z direction, or here it is in a y direction, is where the motif has been placed. So that is why it is put as plus sign. Then if you do a twofold operation, okay, this will get repeated itself here, it will come, and on the other side, okay. And that means that around this twofold, here is twofold, here it is twofold, here. This shows that how when the motif is being placed, the crystal is being generated. All the atom positions in the crystals are being shown, or the pattern position is being shown. But now if we look at it, in this particular position at the center now, there is a twofold axis has come. Now one which has come here, another which has come here, right. So then there will be correspondingly here as well as here. So other positions also twofold rotation has been generated, correct. This twofold rotation, if we look here, what is essentially important is that though this is the in 2 dimension the unit cell which we are representing it, if you look from symmetry point of view, this is the lattice. By doing a symmetry operation, we can generate the full unit cell itself. So when we have to work on any system, if we know the symmetry which is associated, we can go to the cell which is much smaller than that. That is, from here to here, if we move within this cell, anywhere it is going to be a one-fold rotation. That is, I move from here to here in some direction. At some particular point, I find that I cross a symmetry point. Okay. So this is what it is called as an asymmetric unit. I will come to it later and explain. Okay. This is how graphically the positions are represented. Okay. So here is a general position. When I put an atom, I will have to put another atom here to represent it. As well, I can put an atom at this position and this position also and generate the lattice, correct. I can put an atom at this position and generate a lattice, or I can put an atom at this middle also and generate a lattice, or I can put an atom at this position also generate a lattice. There are many possibilities exist. These are all the possibilities we are given in this positions, where general position as well as the special positions are given. This is the information which is very much necessary to construct crystal structures. Okay. So for the general position where the symmetry is one-fold, the position if it is x, y, z is there, by a twofold rotation it will go to x bar, y, z bar. Okay. That is the position which will be generated for the other point when one point. This is an equivalent position which you have generated by symmetry related. Other position, like if I consider it as the center here, the center here, what is the symmetry which is going to have? It is again a twofold symmetry. Okay. So the number of atom positions which will be required is only one, and that is given by this position 0, y, half. No, no, if you consider this one, 0 is along the x direction 0, y direction, okay, some distance which you have moved, no, just a minute. Here what essentially is that y is along the z direction, right. So if you consider that, okay, this is 0, okay, A direction 0, Z direction half, okay, Y direction. That means that this point, I can put one here, or this point if I choose it, then it is going to be this particular position gives where the atom could be placed or the motif could be placed, and here it is going to be half Y half. So, all the symmetry points if we place it, these are called special points, okay, any one of them we can keep it and generate the lattice. So, these are all the options which are available. When we have the unit cell, when we know the symmetry which are associated at different points, then by putting atoms or motif at some of the symmetry points or on a general point, in short means that anywhere within the unit cell, what all positions atoms have to be generated so that the structure will show twofold symmetry, right. This is what essentially is being shown, the various points, okay. Here what is being done is that in a monoclinic lattice, if it is instead of 2 it is 2 1, that is a screw axis is present, then this is the symbol which is being used to represent screw, okay. Okay. And in this case also we can find out how the atom positions are, okay, coordinates of the positions we can find out. Here there is going to be only one position which will come. I will not go into the detail in this one because I will explain it with another structure. There is a way in which mathematical operator which is being used for representing screw and glide. This is called as a sites operator. What is it done? It is RT, okay, this is how it is being shown. What it means is that the capital R represents the point group symmetry operation, this T represents the translation operator, okay, and this is being done on any point. If you do that, it will be equal to R into R plus T the translation. This shows how that given one position we can generate the equivalent positions. Suppose this R is going to be an identity operation, okay, the translation is 0, means that what it happens, we are whatever we do it's in the same point, right. That is how it is called as an identity. Suppose identity is there, instead of 0 this translation is Tn, means that in some direction. So, that means that only translation is being performed. Like here if we put a symbol M100 and then the symbol which is being used is that what is the glide which is going to be there. This means that mirror which is acted upon, first you generate that position to which you add the glide one, then you get the coordinates of the other equivalent positions, okay. This is how it can be done. Now, this is the structure which we will take up, because we talked about the point group symmetry 4 mm. Now, let us look at a crystal which has got the space group symmetry, that is a primitive lattice we are taking. It is the simplest case to consider P4 mm, okay. What are the symmetry elements which are there in the unit cell? Every lattice point will have a 4-fold symmetry, correct. At the center another 4-fold symmetry will come. Then on the edges at the center there is going to be a 2-fold symmetry. Then if you look at it across this axis, if you put a mirror, then we will have a mirror symmetry. Along this also, along body diagonal also mirror comes, correct. And then along these two axes also mirror is going to be there. 3 types of mirrors are going to be there. Then this generates what is called as a glide. What is a glide? Essentially, if I take a point here like this, okay, where an atom has been put, it is translated by this distance, and then I take a mirror of it across this direction, it will be generated. Then again I translate it by the same distance, half of body diagonal, and then again take a mirror, it will come into this point. So, that way also, that is why here when we look at this particular structure, okay, as a consequence of putting of atom at different positions, the glide is inherently generated. In some structures the glide comes separately, inherently they are not present. Okay. And if we put an atom around any particular position, okay, random position we are putting an atom, then when we do the full symmetry operation, okay, then all these 8 positions will be generated here. Okay. That is, this is what it is, 1, 2, 3, 4-fold rotation. Then we take a reflection, because the reflection is generally the symbol which is used is within the circle a comma is being used. Okay. So that means that 8 positions are there. So everywhere you will have an 8 positions which are going to be there. Okay. Now what is essentially important is that around this is the origin. Around the origin, if I am moving it, okay, at a random position, if I am putting a motif, what is the space within which I can move the position before cutting across any symmetry operation? That is what the asymmetric unit represents. That is within this triangle. If you look at it, anywhere if I move it, there is no symmetry element, I will be crossing it. If I reach at this y direction, y value greater than half, I will be crossing it. Here if I move it, but what is the value which x can have, because this is the diagonal. Na? So at any particular value, the x should always be less than y. When x becomes y, I will be, where is the point it will be, x becomes y will be on the body diagonal. That is a mirror point it has again, it is a symmetry point it has reached. Okay. So asymmetric unit is essentially this. Using this asymmetric unit and applying the symmetry, we can generate others. That is, this becomes very important when we do many calculations. Even on computer, when you wanted to do some calculations, what you have to do it is look at the symmetry, then the symmetry dictates what is the lowest structure on which we have to do the calculation. Then using the symmetry operation, quickly we can replicate all of them and generate the full structure. Exactly the same thing is being followed here also. Okay. And then these are all the symmetry operations which are given. What are symmetry operations we have? When we say 4 mm, 1-fold rotation is there, 2-fold rotation is there, there are 3 types of mirrors are there, right? Then 1 4-fold rotation, okay, and the positive direction as well as negative direction. So total 8 symmetry operations are possible. Okay. And if we try to put atoms and positions, now we consider atom or a motif as a general position. We can put it at any of these special positions also. If you try to put at special positions, how many atoms will be required or how many positions the motif should be kept? That is what the information which is being given here. So, like here if you look at it, what is the symmetry associated with it? 4 mm. At this center 4-fold, there is a 4 mm symmetry. If you look here, it is a 2 mm symmetry. Then what are the positions it has to be kept? All this information is given. This is the table which is extremely useful to generate crystal structures. Okay. Now let us look at it in a little bit more detail. In this what I have done, it is the same figure I had taken it. Okay. I had shown that what is A represents, there is some way to represent the symmetry elements. Suppose 2 symmetry elements are there, 4 mm at 2 different positions. How do you differentiate? So the y-cuff come out with an that you serially label them A, B, C, D like that, so that will distinguish them. So that is what essentially is being done. Okay. Then how many equivalent points are there? There is only one in the case of 4 mm. So that is what it is being shown. And where the B is this position, C is going to be this position, D is going to be these two, okay. E is this mirror, okay. F is going to be this mirror, G is anywhere within this one, you can take a point, right. That is where it is a general position. So here you will look at it in the table, if you see it will be in the multiplicity, y-cuff letter and the side symmetry. That is in the unit cell at different places. If you look at it, the lattice has got some particular symmetries which are associated with it at different positions. Okay. We can put atom at general position or at specific position, anywhere it can come. We are talking about we are placing an atom there, but actually what happens is that depending upon the type of interaction, okay, atoms the type of atoms which are being present, they will try to occupy preferentially some positions. We are trying to look at it, what are the possible positions which the atoms can occupy in the lattice, correct? Okay. So here what I have shown it is, what are the possible positions if we are trying to put an atom it can occupy. Suppose I put an atom, only one type of an atom is being present, and I assume that it's an atom is a circular one or spherical one, so that we can consider that it has got an infinite symmetry associated with it. We can place it at this position. If we place it at this position, by translational symmetry, when we place it at origin, this position and this position will be generated. So all these positions will. So if we keep it there, now this structure will have the full symmetry will be there, 4 mm symmetry, correct? One atom we can keep it here. With respect to origin which has fixed, instead of it, I can put the atom at this body diagonal. That is, if I keep it here, no sorry, if I keep it at this particular position, then what happens? Then also, okay, only one has to be kept here. By translational symmetry, we will be able to generate another one will come here, another one will come here, where the centers of other unit cells. So that way also it is generating the full 4-fold symmetry will be there. But within the unit cell, only at one position we have to keep it. Suppose now we are trying to keep the atom not at these two positions, we are trying to keep it at this symmetry point. Then I will have to keep it here and here, okay. By translational symmetry, these two will be generated. Now you look at this in this unit cell, this has a 4-fold symmetry, along this has a mirror, all the symmetry elements are going to be there, correct? But how many positions we have to keep it on the unit cell? 4 positions, correct? That is true with respect to another, this one here 4 has to be kept, but this 4 have to be kept at these positions, the body diagonal. And in this particular position, here what we are keeping it is, one is kept here, okay, and another will come, 8 positions will come, but essentially equivalent how many will be contributing to the unit cell? Here again only 4 will be there, because the faces are shared by 2, correct? And here again if you look at it within the unit cell 4, now this is also, so all of them satisfy the symmetry which is 4 mm symmetry, but the place where we are keeping the motif at different places. But the number of atoms which are required is changing. Here it is only one position is here, one position. Here 2 have to be required in the unit cell. Here 4 have to be required. If we keep it at a general position, 8 positions, because you see that within the unit cell 1, 2, 3, 8 are there. So 8 equivalent positions atoms have to be kept. Then only if we keep anything in a general position to satisfy this symmetry, other 8 equivalent positions are there where also the motif has to be kept. That is the only way we can generate. So all possibilities exist. Fine. Now let us look at what sort of a, suppose the motif is not an atom which does not have an infinite symmetry, it has some finite symmetry, then where will we keep it? That is, if it has a 4-fold symmetry, the motif which we are trying to generate the lattice, the crystal has got a 4-fold symmetry, it can be kept in this position or this position or at this position, only these 2 options are there, right, because those positions the symmetry which is there 4 mm symmetry. If I keep at this position or this position, it has a 2 mm symmetry. That means that the motif itself should have a 2 mm symmetry should be associated with it. Then this shape of the motif gives a twofold rotation and a mirror is also there. Then if this is the way if you keep it, now you can see that again a 4-fold symmetry is satisfied. In this particular position if I try to keep it where a mirror is there, the motif should have a mirror associated with it. Otherwise this if we keep it in this particular fashion, 4 mm symmetry is being satisfied. Here this is the way in which it will come. It will come. If you take an asymmetric motif, if you try to keep it, then this is the way the motifs have to be kept to satisfy the full symmetry. Okay. from this we can understand, okay, that there are various positions in which atoms could be kept, and the number of atoms which are required to be kept on different positions also changes, okay, from 1 to 8 in this particular case.
Like in 4D case,
Yeah.
should the motive also have a mirror symmetry? Why can't it be like the case in 2C?
No, 2C also has got a mirror symmetry which is associated with it. It is inherently there, but it's not explicitly clear. That is why I drew this diagram to show it.
You can have the same thing.
Yeah, there are some structures which you can have a twofold rotation, but need not have a mirror, right? That is the only reason why I do it, to show the distinction that now this has got a mirror is also associated with it. In fact, the same thing could have been put here also, correct? Okay, suppose we assume that there is only one type of an atom is there, okay? We know the lattice, we have to put place the atom at any lattice point, either at a special or general, and generate the lattice. Energetically what will happen? It will try to choose the position where the symmetry is maximum. That means that minimum energy is required, or the number of atoms which will be required is only one. So the two options which are available now is either in this one or this particular one, correct? Only these two positions it can choose, correct? Others are going to be energetically it is more atoms, so it is not a probable one. That is the way which can be chosen. But geometrically anything it can choose, because if we do not consider energy, correct? So that is why I had given all the positions we can put that atom in any position and generate the lattice. It will have the 4 mm symmetry. Suppose you assume that there are two types of atoms are present, okay, and an atom A and B, okay, and the stoichiometry is AB. Okay. If we fill all the A position with this particular type of an atom, lattice position, then what is the option B has? Because since the stoichiometry is being maintained, if it comes to this particular site, the number of atoms per unit cell for both of them is 1. This is the only option which is available. It will choose that position. Okay. Or suppose we are told that this is the stoichiometry of the alloy, and this is the space group symmetry which the crystal has got, then now we are able to find out which positions the atom should be placed, correct? We can construct the crystal structure from this information looking at this space group table. Is it clear? Suppose it is AB2, the stoichiometry is, but still the symmetry has to be maintained as 4 mm. Then what is the option which we have now? The first atom could be placed in these positions, correct? The second atom could be placed in these positions. These are the only positions which are available. B atom has to be placed here, or the A atom could be placed here and the B atom could be placed here. This is also possible, because for the A atom there are two possibilities exist. B atom, the possibility is only this which is defined. Now which position these atoms will take depend upon the type of bonding which is being present. Okay, there are many various ways in which it can consider it, but geometrically A can occupy either this particular position or this position, B can occupy this position. Now the stoichiometry is being maintained. Correct?
We need 2B atoms, right?
2B atoms, because one atom will come here, another will come here. Okay. This is, the others are generated by translational symmetry. Now suppose it is AB4, still maintaining 4 mm symmetry. Then the options which we have is A atom can occupy this position or this position. What are the positions which B atoms can occupy? Either this or this one or this one. 3 choices are available, right? That will give rise to AB4 stoichiometry will be given. Now which position they are going to occupy, how to find out, that is the game where X-ray diffraction has to be used to find out what is the type of bonding, what is the radius of the, if it is especially in ionic material. Ionic material is much simpler because you can consider each of the cation or anion as a hard sphere, okay, so that if they come close together they cannot interpenetrate it, and from the size itself we can find out what should be roughly the lattice parameter. That way we can find out where exactly they will come. Otherwise in the case of a metallic sample it's going to be, it's not that easy to tell which position, but we have to do some calculations to find out which will be energetically favorable. Okay. But this gives the options which are available, only in one of these positions it can come. That is, the A atom has these two options, B atom has these two options. Which combination is going to work? Now at least we have narrowed down. Using this, we can tell that these are all the positions where it can come, correct? This is the advantage when we know the symmetry, what are the symmetry elements which is associated with it, okay. So what I had given is that the criterion for placement at atoms at different positions, that depends upon the energetics, right, so that the overall the energy is being lowered. That is the criterion which will decide out of the possible geometrical possibilities which we have, that we have to find out. Suppose there are 3 atoms are there, then also you can try to find out, okay. Like here if you take the 3 atom case, A atom can occupy this position. If B atom occupies this position, it will be AB2. If C atom occupies these positions, then it will be AB2C4 will be the composition of the alloy, right. From this I think you have got a fair idea of how at different places one can place atoms, or suppose I tell that this is the space group symmetry, this is the stoichiometry of the alloy. Now you can find out which are positions that which atom has to go so that the symmetry will be maintained. This is how this table, or you can understand that using this table, okay, if we are to construct a crystal, what we require, this parameter alone is not sufficient, lattice parameter is required, okay. All those aspects of it, what are other things which are required, okay, and how we will go about and constructing it, we will talk about it in the next class, okay. So essentially what we have covered today is starting from point group symmetry of a particular point group symmetry, okay. We have considered how the space group generates, okay, that what are the special and general positions, how atoms have to be placed around these general positions or special positions, what sort of symmetries which should be associated with it if we are placing a motif around these positions, okay. All these details we have looked at it, okay. We will stop here.